So in simple linear regression, we've got a single input feature, x, from which we want to predict a scalar output, y. In multiple linear regression, we're actually going to have multiple input features. So instead of having just an x, you could have a x1 feature, a x2 feature, x3 feature, ... xd feature. And from this set of multiple features, we want to predict a single scalar output. You can think of bunching all of those features together into one vector, which is then a feature vector from which we want to predict the scalar output y. In this video, I will start with an example, basically motivating this multiple linear regression setting. And then we will start to go through the mathematics. You've actually gone through all of the steps already that you need. So in this video specifically, we'll start with the first two steps, which is explicitly defining the model and choosing an appropriate loss function. And then in the next video, we will look at how you actually optimize this loss function with respect to the parameters. So these steps are exactly the same as the ones we followed for simple linear regression. We're just going through the same steps for multiple linear regression. So this slide shows a plot of the so-called Boston dataset. Each point in the plot, each one of these dots, represents a single neighborhood in Boston. The plot shows the median house price in units of $1,000 for 506 neighborhoods in Boston. This median house price is shown as a function of two variables: the average number of rooms that you find in a house in that neighborhood, and the percentage of households with low socioeconomic status in that neighborhood. So for example, this point, it's a little bit hard to see, but if let's say we track down and we go here, then this neighborhood would have 4% low status households in that neighborhood. And then if you trace back here to this point, maybe just over 8 rooms per house in that neighborhood. So maybe just stare at this data for a little bit. What does the data seem to show? It's maybe a bit hard to see because it's in 3 dimensions and you can't rotate it. We've got this fixed view, but maybe you can identify a general trend, for example, for how house prices change when a neighborhood has more or less lower status households, right? How does this price change if we go towards this end of the plot or towards this end? Does the general trend that you just observe from the data here, does that match with what you would expect? Does that match your intuition? Now, say we want a model that takes as input the average number of rooms and the percentage of low status households in a neighborhood, and then outputs the median house price for that neighborhood. In this case, we have more than one input feature. We can maybe call the average number of rooms in the households. We can call that x1, and we can call the percentage of low status households in the neighborhood, we can call that x2. And the thing we then want to predict, our target value, is the median house price, and we call that y. So we will try and use multiple linear regression to solve this problem. Let's first look at the general definition of the model and how we learn its parameters before coming back to this example of the Boston house price data. So for the general case of multiple linear regression, we can have up to d features, a x1, a x2, x3, up to xd. And from those d features, we want to predict the scalar output y. So in our example of the Boston house data set, we've got 2 features, but you can have more than that. So a multiple linear regression model will predict the output as a linear function of all the different input features. So let's just write that down. So as before, we denote our model as f. And in this case, the model takes as input a x1, a x2, and in the general case, up to xd features. And this model will have more parameters than we had in the simple linear regression case. We will have a w0 and a w1, as we did before. But then we will also have w2 up to wd. And the output of the model in this case is equal to w0 plus w1x1 plus w2x2 plus ... plus wd xd. So the output of the model the output of the model, is a linear function of the different input features. So simple linear regression is actually a special case of multiple linear regression where our capital D is just equal to 1 because we only have these two terms. In the case where we have two input features, a x1 and a x2, this model would actually define a flat surface as the one shown in this figure. And you can maybe think a little bit how W0, W1, and W2 in this two-dimensional case would impact the surface. The parameter W0 is sometimes called the bias term, because it basically would shift this whole surface up and down. The other parameters, W1, W2, up to WD, they really weigh the different input features. And in the two-dimensional case, this would impact basically the tilt of this plane. We can actually write this model in a little bit more of a condensed form. So here we've got our model again, but now we've stacked together all of the parameters into one parameter vector, W. And similarly, we've stacked together all our input features into a feature vector, X. And then you can express the output of the model simply as W transpose times X. And that's really just the dot product of W with X. To do this, we actually had to use a little hack to define the feature vector X. The parameter vector W is really just all the W's stacked together into a column vector. But for X, we had to pretend that the first element is equal to 1. Otherwise, this equation doesn't match this equation. So I should say that this hack is very often used to simplify the notation in machine learning models. But unfortunately, it's not always used. So sometimes it would require a bit of reverse engineering on your part to figure out whether the writer or the authors are actually doing this or not, whether they are pretending that the first element in X is equal to 1. I will try to be explicit in my videos and my notes and tell you whether I use this shorthand or not. But if you're not sure, definitely make sure that you ask a lecturer or a friend. So now the question is, we've got our model written out. How do we actually choose W? How do we learn W from the data? So we're given a data set of points of previous input-output measurements. So in this figure, for example, here we've got one data point, which has a certain input value, and then this target output value. And in this case, we actually have 1, 2, 3, 4, 5, 6, 7 points. And from these points, we want to figure out what is the best setting for W. How do we basically wiggle the parameters of W so that our surface fits the observed data well? To figure this out, we of course need a loss function to tell us whether a particular setting for W is good or bad, given the data that we've collected. And as in the case of simple linear regression, we can use the squared loss function to tell us how good a particular setting of W is. So here, as before, we've got our loss function, J, which is now a function of the parameter vector W. We sum over our data points, and this is the actual observed target value. And then this is the prediction of our model for this particular input X little n. And then we take the difference between those two and we square it. And that's the squared loss. We can write that out a little bit more completely so that we can just see the different parameters. And you see here that you need to figure out what W0, W1 up to WD is for this model to be a good fit of this capital N data points. So in the figure here, if let's pretend that our setting for W defines this plane as it is here, what would this loss be? It will basically be, let's take the first data point here, y1, and let's say our model is defined according to that plane. So the prediction, given the input features corresponding to y1, might be somewhere here on the surface. And then this will be the error or the mistake that we're making. For the other data points, we might have different errors. And this squared loss will basically be the sum of the squared distances of my output from my model, the prediction, to the actual observed data point. So if this is my observed data, then this point here, that would be the output of my model for the first input given my setting of W. So we want to find the setting of the parameter vector w that minimizes this loss. So for this example figure here, intuitively we want to wiggle the surface, which is determined by the parameter vector w, so that the squared lengths of these red lines become as short as possible. The strategy that we will follow is that we will take the derivative of the loss with respect to each of our parameters, and then we will set that equal to 0 in order to find the minimum of the loss. This will really give you a set of d+1 equations that you want to solve jointly. So are you looking forward to taking this function, taking the derivative with respect to w0, w1, w2, wd, and then solving all of those d+1 equations jointly? If you're like me, you're probably not looking forward to that. So let's rather follow a different strategy, which comes down to exactly the same thing, but will make our lives a lot easier. So what we're going to do is, rather than doing it term by term, we're going to write the loss in a vector form, and then we're going to find the derivative of the loss j with respect to the parameter vector w, and we will do that directly in a vector form. But what does it mean to actually take the derivative of a function with respect to a vector? Remember, this function outputs a scalar value, the value of how good or bad the setting of w is. But what does it mean to take the derivative of a function with respect to a vector? So here I'm going to ask that you quickly pause and go back and make sure that you've watched my video on vector and matrix derivatives. Then when you've done that and you're absolutely sure you know what it means to take the derivative of a function with respect to a vector, then jump back here and we'll go on with the rest of the video. Welcome back. So our goal is to minimize this loss function with respect to w. We can write this out directly in vector form like this. And as a reminder, remember that the first element of this x vector, we just pretend that it's equal to 1. So what we will try and do is write out this whole summation thing here just with vectors and matrices, and then we will take the derivative of j with respect to w just directly in vector form. So to do this, we're going to define a few matrices and vectors, and then we'll take the derivative. So what you do is you define this big matrix X, which really takes together your entire data set, or the inputs for your entire data set. So what you do is you take your first feature vector and you put that there, your second feature vector there, up to the nth feature vector. And normally we think of feature vectors as column vectors, so we take the transpose to turn them into row vectors. Similarly, what we do is we take all our targets, the first target, the second target, up to the nth target, and we stack them together into a target vector y. X is normally called the design matrix, and y, you can just think of that as the target vector. Now, if you do that, then you can write this function here in this form. And that form only contains vectors and matrices. There's no summation. To see how you go from 1 to this equation 2 might be a little bit hard. So I'll just quickly help you to see that. What you can do is you can define an error vector E, which basically stacks the mistakes that you make for each of your items in your data set. So here's the mistake for the first training item, second up to the nth, and you stack all of them that way. And then you need to go and do this on your own a little bit, but go and convince yourself that this equation here with the summation, that can be written as E transpose times E, or the dot product of E with E. Right? It's not that hard to see. If you take the dot product, it's just this squared plus this squared, this squared, which is exactly this equation. And now, if you've paid attention, you can actually write E using these definitions. So E is equal to y minus x, our design matrix, times w, our parameter vector. So that means that if you plug this into this little equation here, then you end up with 2. Okay, so why did we go through all of that effort? We now have a form for the loss function j containing only matrices and vectors. And this means we can just use our vector and matrix derivatives to determine the derivative of the loss with respect to the parameter vector. To do this, before we take the derivative, I'm just going to multiply out j and w a little bit more. So here I'm just multiplying out the terms. And it's useful to remind yourself that j is really just one number, right? It's a scalar number. So if you're going to multiply out all this stuff, then you need to end up with a 1 by 1 matrix, if you want to think about it in that way. So we multiply out all the terms and we're left with this result. So in this video, we've defined the model explicitly and we've chosen a loss function, and then we wrote out that loss function in matrix form, as you can see on this slide. So in the next video, we will finally actually take the derivative of the loss function with respect to the parameters and find the optimal setting of this parameter vector W.